In our second talk for the session Human-Robot Interaction, we have our speaker, Dr. Xin Yu. She's a faculty member at the Robotics Institute at Carnegie Mellon University. She's passionate about creating persistent robots that can coexist and collaborate with humans in shared environments. And the title of her talk is Core Challenges in Navigation in Human Environments. So please, the floor is yours.
Thank you so much for the general introduction. So today I'll be talking about the core challenges of social navigation. Okay, so let's first look at this example to see how difficult the robot navigation in the real world is. So, okay, so if we watch this scene, there are a bunch of static obstacles. There are obstacles that are not moving, and it can be large or small. And then we also see a lot of moving obstacles, including people. People are walking or on a bike, or driving a car and so on. Okay. So it's getting more and more difficult. And then if we watch this scene a little bit more, then we also realize that there are invisible rules too. So there are, in this example, it's hard to see the pattern, but we do see the cars from the other side moves to the other, from one side to the other, and so on. So there are traffic rules that people follow. And then there are also more subtle rules that people generally follow. So how much distance people keep between people and so on. Okay. All right. So today's topic is within this navigation in dynamic environment, but more focused on how to make the robot navigate in a human populated environment. So we will focus on the pedestrians, which is one of the types of dynamic obstacles, and then how to make the robot to choose actions that are socially compliant. Okay, so just to go over some of the definitions. So for the robot navigation, this is essentially a planning problem. So when we say navigation, there is typically a goal to destination to reach. And given that goal, the problem is to find a sequence of actions to move from the initial position or the current position to reach the goal. And there are usually cost or some objective to optimize. And in the autonomous navigation domain, the major objective here is the efficiency and also the safety. So this is a bare minimum. In order to get to the goal, we need to find a path that is efficient. And while we are going, the robot is reaching the destination, collision should be avoided. Okay. And then when we move to a more human populated environment, there are additional constraints or objectives. So comfort is one step more than safety. So for instance, if the robot avoids a collision by like maybe with a very, very small gap, that's still considered safe, but it generates discomfort. And then also, even if it's safe, the behavior can also disturb humans. So for instance, if the robot is changing directions too frequently, then people will not feel safe around it. Okay. And generally, under this problem category, people have worked on the pure navigation, which again has a strong objective to reach the destination. And then it's mostly done in the ground vehicles setting. So for now, so the traversability became an important part of the research. So how to find the cost for different types of terrain to navigate over. So, okay. And then the next thing is the pedestrian prediction. So this is not a navigation algorithm. So you can, you notice that there is no notion of a goal, but if we watch a crowd behavior, we can still predict where people are possibly going. So that's this problem. And then the objective here is if we want to predict the naturalness, how people move, this is the focus of this research. And then in this category, there's very few existing work that's actually focusing on the environment. So that is the difference between the traversability focused navigation versus pedestrian or human oriented research there. And then the social navigation is a little bit of both. So it has a strong notion of a goal. So we still want the robot to be able to reach the destination while observing these social rules and also get these safe actions. Okay. And then unfortunately, even in this domain, the social, the environmental context is largely ignored. So if anyone's interested in doing research on these topics, including environmental context would be a very good direction here. Okay, so I will first start describing work on the pedestrian prediction a little bit, even if it's not navigation. Okay, so just to summarize what has been done in the recent years, so there were a lot of existing work on using non-parametric method before deep learning. And after people started using these deep learning approaches, mostly recurrent neural nets and LSTM. So there were a lot of interesting work, and these are great, but these are predictions. So it's not, we can use these algorithms for robot planning, for instance. But these are still very useful because the robot navigation algorithm needs a social interaction model. And these model, the pedestrian prediction model can be used for that piece. Okay, so I'm going to use the social attention, one of the approaches that Anirudh, one of my students, developed. So the assumption here is when people are navigating in a human crowd, they attend to maybe not everyone in the same environment, but maybe a small subset of other agents, but they're not necessarily the closest neighbors. So that was the initial assumption to begin with. Okay, and I'm going to explain how these pedestrians are modeled in our framework. Okay, so in this example, you see 4 people. So it's a fixed time step. So at one certain time step, you will see these 4 people in different spaces. So these blue edges actually represent the spatial relationship between the 2 agents. So these are fully connected graph. And then if we include one more time step, so the next time step, then what we can see is the temporal relations. So for instance, this first agent was here at time step t, and then at time step t plus 1 is at a different location. So how this the spatial relationships are represented. Okay, so if we use some graph model here, so spatial temporal dynamic graphs, the idea is a very classic approach. So it can abstractly represent a lot of different informations that has a spatial constraints and temporal constraints. So in our case, we will use 3 human example here. So there are each node kind of represents the position of the pedestrian. So as we saw in the other illustrative example, and then the temporal edges are included here too. So this is more of a kind of abstract representation. And then if we unroll, then we can see kind of similar structures. So the blue edges represent the spatial relation between the agents, and the green edges capture the trajectory. So it's a temporal changes over time given one agent. So agent U at time step t and agent U and time step t. Okay, And then, as I said, the blue edges are the spatial relations. So these model can capture these interactions in the space. So that's a very abstract representation of this navigation prediction problem. And for the actual implementation of the idea, we can consider many different types of implementation. And for now, we will consider the deep learning neural net-based approaches. So there are options. So we can either use a CNN or RNN-based ones, for instance. And typically, CNNs are used for structured data, which images are good examples. And the RNNs are used for processing sequential data. So the trajectory is kind of a bit more of a sequential data. So people have used the RNN-based method more. Okay, so just to quickly review, if we use CNN, so then we can see this input as a trajectory, and then we can apply one-dimensional CNN. Then the output, so given the input trajectory, the problem is to predict the output, which is the future trajectory here. And then the output will be represented in a function of a neighboring inputs in this 1D CNN. So something like this, okay? And then in the RNN case, this input is sequential and the output will be generated using the sequential input and the previous prediction. So it just illustrates the difference. Okay, so for social attention, we use the RNN-based method. So there was a proposed RNN implementation called the structural RNN, which uses the spatial temporal dynamic graph. So in their example, the problem domain was different. So they were modeling this person manipulating objects. So the nodes include heterogeneous types. So there is a human node, the object node, and then the edges are representing the interaction between human and objects or objects and objects. Okay. Okay. And then, so for social attention, so we use this structural RNN to implement the idea of a spatial temporal graph for the pedestrian trajectories. And then the key idea here was using the attention module. So again, we'll just see what is the attention mechanism. So probably many of you are already familiar, but just to review. So attention mechanism was introduced to capture a little bit more sophisticated information for the context. So if we encode the input into some context vector and without having attention, it will be some key information can be lost. For instance, the temporal dependence. Okay, so the attention mechanism can make the model to focus on subparts of the input more carefully. Okay. So how do we implement this attention mechanism? So attention just looks at the input as a structured representation, something like a context vector. And then it is essentially another neural network to map this hidden state to the context vector. So it's another function approximation. Okay. So just to quickly go over. So this is another neural net that's representing the attention function. So the attention weights are learned during the training. And there are two different types of mechanisms we can use, a soft attention or hard attention. So the difference is soft attention is more like a distribution over or possible context vector. So it's a smooth and it's naturally preferred because it's a good choice for the back propagation as it's differentiable. And the hard constraint, hard attention, sorry, is choosing just one best match. So in this case, how do we use it for the neural net? So to make it similar to the soft attention, sampling method can be used. Okay. Okay. So going back to the social attention idea, so we represented the trajectories using the spatial temporal dynamic graph in a structured RNN. And remember these edges coming from the other agents. So these blue edges are the ones that we care about because that's going to be the social interaction model, okay, at a fixed time step. Okay, so here what we are trying to do is whom these agents should pay more attention to. So that naturally maps to the idea of attention model over all possible agents. So this algorithm is more scalable in terms of the in the number of agents. So so that's a difference between another popular method called the social LSTM. Or the variants of social LSTM that only uses the social grid, which is close neighbors only. So, okay. And then these are some of the illustrative examples. So in this example, the agent is here. So it just shows the agents that are far away doesn't really matter. So they are more or less equally important. And then the agents that are staying in the same position are least important. And then this example, it's a little bit more clearer. So the agent is passing by. And this agent, the green dot is the closest one, but the agent doesn't pay attention too much to this one because it's not moving. Okay, so that was the recurrent neural net based like approach, like the sequential model, and there are recent approaches using convolutional neural nets. So the hypothesis here is the majority of these RNN or recurrent models, including LSTM, will gradually add more noise for the long-term prediction because it propagates. So the idea is maybe for the longer-term prediction, CNN models would perform better. So Eagle, one of my students, tried the idea and it actually was the case. So it performed better, slightly better. And then almost at the same time, there was another paper very similar came out and their conclusion was also the same. So there is no like strict winner here, but there are some benefits of using CNN. Okay, so when I said there was no clear winner, because the performance in the current evaluation benchmarks are reaching the saturation point. So we see a very, very minor improvement, but all the algorithms are working well. But does that mean we solved the problem? It's not close to solving the problem at all, but why is this happening? So that is one of the challenge that we want to address. So that's because all the research benchmarks or data sets or evaluation methods are maybe too simple. But now we are moving to the social navigation part. So that up to that point, what up to this point was about the pedestrian prediction. So we will use that to model the social interaction for the navigation algorithm. All right, so under social navigation algorithm, again, many different ideas have been tried. And just for today's talk, I included only three big areas. So one is using learning from demonstration. So inverse reinforcement learning is watching people doing the same task and then try to recover the reward or the penalty function. Okay, so naturally, the objective for this type of approach is more focused on the naturalness because it's learning from the human's natural behavior. Whereas the reinforcement learning approach, it starts with some fixed reward or penalty function. So we need to have a model, or well, there are model-free approaches too, but the assumption is there are more clearly defined rewarding system. So for instance, collision avoidance. So the algorithms that's based on reinforcement learning are performing very well, ensuring the safety of the agent behavior. So, okay. And then, but the drawback is by trying to be natural, sometimes these IRL-based algorithms will violate the safety constraints because it is, in order to avoid the collision, sometimes you have to make a quick turn, which doesn't look natural. And then the RL algorithms, the same for, it's a complete opposite problem. So in order to be safe, it loses the natural behavior. So it looks like more robotic, I say. Okay, so the approach that we have tried was, can we achieve both? So, okay. So this idea of this navigation is having multiple terms. So this navigation is in essence, it's a decision making using multiple objectives. So it's never a single objective. I want to reach the destination and ignore all the other constraints. So there are this self-interested objective that is trying to reach the destination as soon as possible. So that is modeled here as an intention force. So there is an intention to reach the goal. And then there is a social compliance. So, well, at the same time, we want the robot to be socially compliant and safe around people. So this part B, the social aware and the public interested objective is modeled as a social force. And then there are some natural stochastic fluctuation, which was included in the original theory of social force. So the terms I will show you in the next slide actually is according to an existing theory called the social force, which has these multiple terms. Okay. And then at the end, what we're doing is, in order to enforce this natural behavior, we had this adversarial training. So the discriminator will decide whether this is human-like or not. Okay. So this last part is very similar to another approach called the social gain, generative adversarial network. So but again, a lot of people are working on the same problem. So sometimes we see similar approaches proposed almost at the same time, but independently. Okay, so this is the social force model that was introduced in the mid-90s. So the good thing about this representation is because of this factorization, it's easier to explain because we can generate like what if behaviors. So if we didn't have social term, how the robot would have behaved. So there is a reason why the robot chose this path. For instance, because of this social force that's to be more safe. In the trajectory prediction and also for navigation, there are two types of evaluation metrics that are popularly used, which is the displacement error, because a lot of people use the recorded data. So on the recording, the only thing that we can do is a comparison. So we make a prediction for one agent given the past trajectory and other agents' behavior and how the population actually moved afterwards. So we can measure the error between the prediction and the recorded behavior. So that's a general displacement error. And you can measure the average over the entire trajectory. That's called the average displacement error. Or you can measure that at the end, at only checking whether there, how much error happened at the goal location. So this final displacement error is checking at the goal only. So it makes perfect sense to use to train the intention force, because that's what the intention force cares about. Okay. And then the average displacement error, which is the more general behavior throughout. So this again makes sense for training social force. Considers the interaction with between agents throughout. So we use this. And then the third term is the safety. So the resistance loss was added to ensure the safe distance. So this is more of a trying to enforce a little bit of a hard constraint. It is not hard constraint, but it is a pretty strong term, so that the robot will at least try very hard to avoid a collision. So without this term, and this is another challenge or the secret of these social navigation algorithms, the majority of the data-driven learning approach algorithms will generate paths that can result in collision. So there is no explicit term to avoid collision, which is very different from robot navigation, where that is one of the major objective. So all these data-driven approaches are considered risky because of that reason. So even if we try very hard, and I recently talked with someone who's using reinforcement learning to solve the same problem, and he also shares the same concerns, how to enforce this safety, like hard constraints. So this term was added. And then the safety distance it also depends on the social context. So a good example is prior to COVID-19, it was 0.2 meter in existing psychology literature, but now it's 2 meter. And when everyone is apart, far apart, there's not much need for caring about this social distancing. And also it's culturally dependent too. All right, so so the overall architecture is now combining all these different terms. So again, there's intention, so the intention to reach the goal, and then try to be socially compliant. At the same time, try to avoid the collision. So altogether, the decision is made. Okay, so this is a qualitative example to show the difference between intention only model versus socially aware model. So in the first one, we dropped the social force term. Then here you can see this red part is the predicted behavior or the chosen actions. And then we can see how close the agent gets to the other agents. And on this side, it's basically the same sequence. And here we can see this agent kind of waits for these other agents to go first. I'll just play it one more time. So here, the red agents wait, and then these other 3 agents go first. Okay, and then we also did some real robot experiments in a little bit controlled setting, and the performance was good, but the findings is, so there was a finding from this robot experiment, which is this is a kind of human robot implicit teaming. So you can see these are people who are watching the robot, and they carefully also try to avoid. So the navigation happens kind of smoothly, but half or even more than half of the job may be done by human participants. And partly the reason is this robot is very small, like a low on its height, and it makes a lot of noise. So people's reaction is very different. So that leads to future directions. So here I'm gonna kind of talk briefly about the identified challenges. So the one challenge was the evaluation. So even for the trajectory prediction side, I mentioned that the performance is saturating, which means we need a better evaluation metrics, data sets, and benchmarks. And the difficulty here is it involves a human. So for other domains, we can use a simulation at least, but human simulators are not very well accepted by the research community, especially at human-robot interaction side. And also to train a model using simulator, if the simulator can model human behavior, then we already have a solution. So it is a chicken and egg problem. But we actually came up with some ideas about how we can leverage simulation ideas for social navigation. So that's a current research that we are working on. That was inspired by this pandemic because we planned to have a human experiments last year, but couldn't do it. So we switched to simulation. So what we did was now that there are so many people working on the problem, there are many different types of existing algorithms for social navigation. So we made this toolkit that has a bunch of different algorithms, and then we can populate Asian crowd using many different diverse algorithms. So we generate diverse population and then just do self-play. Self-play is a mode, I'll take that back. So self-play is all agents use the same algorithm. So we have a self-play mode results for each algorithm. And then the other set is a mixture of the different algorithms, and then just simulate random behavior, like going randomly assigned goals, and then the agent kind of try to move. And then we defined a set of evaluation metrics to measure how similar these simulated humans are to the existing human data sets or other human behavior. So that way we can generate simulated population that is a little bit similar to existing data sets, but we can generate a lot more if needed. Okay, so that's a general direction we are heading. And then also, probably you have noticed how the problem is formulated in the research community right now. So it is mostly trajectory based. So that means each pedestrian is modeled as a single dot in a space. So at each time step. So, and then over time step, it becomes a trajectory. So that means we don't use visual context, and we don't use environmental context either. So how should we include these to further improve? So some people may think that, why do you use such a simple setup? So the thing is, even if we simplify it to that level, trajectory level, this problem is still NP hard. It is a very challenging problem. So if we add more additional features or the context, the problem becomes more and more difficult. And at the same time, it becomes more realistic. So we are tackling additional challenges to get closer to solving the real world problem. Based on the robot experiments with the humans we ran, one thing that we noticed was the human reaction side. So that's the topic maybe the researchers in more human-robot interaction side might be more interested. So how to analyze the human behavior depends on the robots, not just the trajectories, but the physical appearance. or noise that it makes. So that has a huge impact. So if the robot looks more like, for instance, if the robot looks friendly, then people will get closer, because looking safe doesn't mean that the robot is safe, but people are easily deceived. So if the robot looks scary, people will be more careful. So we didn't intend to run that kind of experiments, but that was the observation from running experiments using two different types of robots. So one was the one that we saw in the video, so like a small size vehicle type robot that's small, but because it makes a lot of noise and also the it moves somewhat abruptly, people are more careful around that robot. And then the other robot was a smaller size, and then it had a narrow torso and it was tall, so it was a child size kind of a smaller robot. And then people even come closer and try to touch the robot too. So it is the very different reaction, and people don't feel scared or like they're taking risk by getting that close to a robot. So how this changing the physical appearance will have impact on the human robot side. So that is an interesting one. And then the other topic that we also want to look at is the tactile sensing. So right now, the robot sensing is mostly for perception, like detecting objects or use RGB to analyze the semantic context. But there is not much sensing. So there is maybe a bumper like sensing at the lower end. So something like the limit switch. So if someone hits the robot, then the robot can stop as a safety feature, but it is not really like the sensing device. So for the social navigation sense, people don't really consider the whole body sensing. So what's it for? But in this example, you see on the corner, if there are so many people and the room is packed, and if the robot has to find someone in this environment, then it is unavoidable. So the robot will touch some other people here. And then if I need to go through, I will, it will be difficult, but I have a way to get past, because there is a different types of actions that we can use. So so far, I only talked about the moving actions, like which direction to go, like how fast the robot should go. But the other action space includes communication. So can robot use conversation skill to ask other agents to take different actions? So it is not controlling, but asking for coordination. So I need to go find someone urgently. So can you maybe make a room for me? So that other agents move because of my action. So it is indirect way to change the environment. So it's a kind of the thing. So if there is something that we want to see changed in the world, then action is the only thing. So we need to take the action to change the world, like the static world, as well as the dynamic, like other people or other agents in the environment. Okay. Okay, so yeah, so that's kind of the wrap up of the social navigation part. And then we recently finished this quite long survey on the core challenges of social robot navigation. So I only touched a brief surface of this article, but if anyone's interested, this is on archive right now, and also under submission for a journal. Okay, and then I'll show a little bit about what my group is doing in addition to social navigation. So as I mentioned briefly, we want to use the simulations for social navigation and also other things. So, and the idea here is the simulation can be very, very useful if we can do it in a kind of online fashion. So if we send the robot to a new environment and let the robot watch how people move around for maybe 5 minutes. And then if the robot can learn quickly, that would be super useful. And the same thing, so if the robot is exploring a new environment and then go to the environment and spend a little bit of time exploring surrounding and then become very good at navigating in that space, then again, so how do we actually speed up this type of online adaptation part? So the idea here is if the robot has this simulation, we call imagination skill on board, then based on the observation, the simulation, new simulation environment can be automatically generated inside the robot's imagination. And then within that imagination space, robot can practice a lot before taking the actual action. So from the outsider, it seems like, oh, with the small, short observation, the robot is doing already good. But it's because it was doing a lot of simulation inside. So there are many technical challenges in this general idea. So that's some new direction that our group is looking. And then for the other side, this is a very high level or intelligence that used to be considered human only space. So there's a curiosity that's getting popular in reinforcement learning. And creativity is even newer. So I'm very interested in working with artists and writers or these creative people. So I have been organizing a workshop on creative AI. So the work on robot painting, for instance, or like generating like a novel using AI algorithms. And so these are very fancy and cool work, but what's missing is from the scientific point of view, the evaluation is extremely difficult. It's only very subjective and qualitative. So how do we actually propose some metrics for evaluating the artifacts created by an AI system? So that's another new direction. And then on the other end, I also do kind of language understanding. So how to use language understanding for the planning purpose. So can the robot make use of the directions or snippets that other people talk about for its own navigation or other problem solving? And then this is our group. So thank you so much for your attention.
Thank you, Dr. Xin Yu, for sharing your research with us. It was extremely insightful. Thank you very much.